In this video, we're going to review right triangle trigonometry. In the pre-calculus textbook, that's section 4.3. We will be going back to 4.2, that's circle definitions of the trig functions. I just like to do them in a different order than the book does. Okay. So I start by just reminding you what it means for two triangles to be similar. Two triangles are similar if they're exactly the same shape, and we achieve that by making sure that all three angles are the same. But they don't have to be the same size, so they could potentially have different sizes. They could be the same size, but they don't have to be. We achieve that if the sides are proportional to each other. So here's an example of two triangles I've drawn that are similar. I can obviously see that this triangle is bigger than that, so they're not the same size, but they're the same shape because this angle is the same as this angle up here is the same as this, and this third angle is the same as well. So notice that the concept of similar triangles doesn't require that we have right triangles. But what's kind of nice about right triangles is here I've drawn two right triangles that are similar to each other. They're the same shape, but again, obviously not the same size. Okay. What's neat about right triangles is anytime I have two right triangles, they automatically have one angle the same because they've got a right angle in them. Okay. So if theta is one of the acute angles, any other right triangle that also has theta as an acute angle in it is going to be similar to this one because these angles are the same, these angles are the same, but I know the sum of the angles in a triangle has to add up to 180 degrees. So this third angle would have to be the same as well. So with right triangles, any two right triangles with the same acute angle in them are going to be similar. Okay. Now obviously these two triangles that I've drawn here are not the same size, but I can see that the sides are proportional because the side lengths of this triangle are twice as big as the side lengths here. So that proportionality of sides, I could set up the proportions a couple of ways. I could say this side here corresponds to this side. So I could say 4 corresponds to 8. In the same way that this side here corresponds to this side, in the same way that 5 corresponds to 10. And you'll notice that both of those fractions, if I write them in lowest terms, are 1/2. That captures the fact, since I put on top the side lengths of this triangle, that these side lengths are half as big as these. And of course, if I'd set it up so that I put the bigger side lengths on top, I would have gotten 2 for that fraction, which would capture the fact that these side lengths are twice as big as these. Okay. Now here I set up this proportion where each fraction involved the same type of side but of a different triangle. But I could rearrange that. I could say 4 over 5 is the same as 8 over 10. When I have a proportion, which is just an equation like this that says that two fractions are equal, that's true if the cross products are the same. So notice when I multiply here, I get 40 and 40. Well, when I rearrange the numbers here, I'm still multiplying the 4 times the 10, and I'm still multiplying the 8 times the 5, and 4/5 is 8/10. This one already is in lowest terms. This one would reduce to that. So here I set up this proportion, but each fraction involved two sides from the same triangle. I just made sure that they were the same sides. And when we do that, we're creating what I'm going to refer to as a trig ratio. Okay. So the trig functions, if I'm using my right triangle definitions, the trig functions just give me a ratio of two sides in a right triangle. And that right triangle is going to be determined by an angle. So what we always do is we label the sides in relationship to that angle. Now, the longest side, which is the side that's opposite the right angle, is always called the hypotenuse. I'm just going to abbreviate as hype, but I'll write out here it's hypotenuse so that you've got it spelled out for you. Okay. Then the other two sides are the legs. Okay. But I can name them in reference to this acute angle. If this is the angle I'm focusing on, you'll notice this one opens up onto the 4. Here it opens up onto the 8. That's why I knew those two sides were corresponding sides. We call that the opposite side. Here I'll just abbreviate that as op. And the other leg we call the adjacent. So the adjacent side is the leg that together with the hypotenuse meets to form the angle theta. Okay, I'll abbreviate here as ADJ. Okay, so what we've done here is 4 over 5, that's opposite over hypotenuse. That's the same as 8 over 10, which is also opposite over hypotenuse. So that ratio being the same just captures the fact that these triangles are proportional. That any two right triangles with that angle in them are going to give me that same ratio if I look at the fraction I create with the opposite side over the hypotenuse. Okay, and of course that has a name. So our three main trig functions are sine, cosine, and tangent. Sine we would denote as sine of theta, and we usually just write out the first 3 letters, so it looks like sin, but we still pronounce it as sine. That's going to be this exact ratio that we just formed. That's the opposite side over the hypotenuse. And I will get the same fraction for any triangle that has that angle theta in it. It will always reduce to 4/5. Okay. Now, different angle, I'm going to get a different fraction, obviously. But if I determine the triangle from one of the acute angles, if it's a right triangle and I know that acute angle, that immediately determines what that one is as well. Okay. Cosine, we write as cos theta. You'll notice sometimes we put theta, which we call the argument of this, in parentheses. Sometimes we write it outside of parentheses. Either is acceptable as long as it's clear that that's the input to the trig function. That's just the adjacent side over the hypotenuse. And tangent, which we'll write as tan, T-A-N, theta, is opposite over adjacent. Okay, so these are the 3 main trig functions that we have, and we form them by simply taking this ratio of sides. This is only going to be defined if theta is an acute angle, because this definition requires that theta be one of the acute angles in a right triangle. So I can't have a negative angle. I can't have an obtuse angle. I can't even have a 90-degree angle or a right angle, because it's got to be one of the other angles. My triangle will have a right angle in it, but my theta has to be one of the acute angles. Okay. There is, of course, a silly mnemonic device for remembering this, and I imagine you're all familiar with this. That's just SOHCAHTOA. That stands for sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. Okay, so let's practice this. I'm going to give you a right triangle, and I'm going to tell you, let's say this side is 6, this side is 9, and that's my angle theta. So I've just given you 2 of the 3 sides. You're going to need to find this third side using the Pythagorean theorem. But I'd like you to evaluate then sine theta, cosine theta, and tangent of theta, and give your answers in simplest form. So if there are any roots involved, you're going to get a root when you evaluate this third side. Simplify that root and make sure your fraction is in lowest terms. So go ahead, pause the video. We'll work through this together, but pause the video, see if you can get this on your own, and then you can check your answer with me when you come back. The first thing I'm going to do here is just label my sides. Okay. So if there's my theta, it opens onto this opposite side. So that's the one I don't know that I'm going to need to solve for in a moment. The 9, that's opposite the right angle, so that's the hypotenuse, and that makes 6 the adjacent side. Okay, so let's go ahead and solve for that opposite side. I'm going to just for right now call it P, because there's a P in the word opposite. I don't like to call it O for opposite because that looks too much like the number 0. Okay. But the Pythagorean theorem would just tell me that 6 squared plus P squared is equal to 9 squared. Do be careful, it's not 6 squared plus 9 squared equals P squared. The 2 legs squared add to give me the hypotenuse squared. So I do need to pay attention to which side is the hypotenuse. Sometimes that's going to be the unknown side that I'm solving for. Sometimes I'm solving for one of the legs. All right, so that's 36 plus P squared equals 81. So I'm going to subtract the 36 over to the other side. P squared is going to be, let's see, 45. So P is going to be the positive square root of 45. Now, it's not necessary to write that positive sign. It's understood when you write this symbol, it means the principal square root. The only reason I'm writing that is to remind myself that if this were an algebra problem, there would be 2 answers, plus and minus the square root of 45. This is not an algebra problem, it's a geometry problem. Side lengths are positive. So, 2 algebraic answers, but I took the one that made sense in the geometric context. Now, this root can be simplified because 45 is just 9 times 5, and 9 is a perfect square. So, this is the same as the square root of 9, which is 3, times the square root of 5. So, I'll write that as 3 square root of 5. And then I can go ahead and get sine, cosine, and tangent. So sine, that was opposite over hypotenuse. So that's going to be 3 root 5 over 9. Now, I can reduce that. When I'm reducing fractions, I want to remember I can't cancel anything under the radical with something that's not under a radical. But I can cancel the 3 and the 9. So this would reduce to root 5 over 3. Cosine of theta, that one I could have actually done before I found P, because cosine is just adjacent over hypotenuse. So that's going to be 6 over 9, which will reduce to 2/3. Okay. And then tangent of theta, that's opposite over adjacent. So that's going to be 3 root 5 over 6. And again, I can reduce because the 3 and the 6 are both outside of those radicals. So this would reduce to root 5 over 2.